Hello friends, so in this week we will look at indoor air pollution or indoor air quality, particularly in the Indian context. So we will have an introduction about the whole topic, and then we will look at specific case studies done for India only. So we will just recap what is indoor air quality and how the outdoor quality affects the indoor health. So if we look at the closer look at main contributions and health impacts of poor indoor air quality, we have first the outdoor air quality, which is influencing the indoor air quality. So here we have the outdoor sources, which are like traffic, household combustion, industry, forest fires, road dust and vegetation, and they can basically go inside the building envelope through different like cracks, which is we have termed as infiltration. And then we can have ventilation types, which we have different operation and types of ventilation systems through which this can go inside. Again, the outdoor sources pollutants can go inside the indoor environment. Then within the indoor environment itself, we can have the number of occupants which may be influencing the indoor air quality, the age and gender, the occupation, the socio-economic status, because that often tells us about how well ventilated the dwelling might be, and the presence and absence of pets. What are the activities of those occupants? Are they smoking? Are they cooking? Are they cleaning? Are they opening and closing windows? Because these kind of things will also bring the pollutants. For example, opening and closing windows can bring the pollutants from outside to inside. Then we have the underlying soil. Is there is it naturally enriched in radon? So it's because it's a naturally radioactive sort of gas. So this radon can also go inside the indoor environment, either through the outdoor to indoor pathway or through the cracks themselves inside. Then we have so these are the things that are bringing things from outside, and the factors related to humans. And then we have the indoor system itself. So what are the indoor sources? What is the building materials? What is the heating and combustion appliances being used? What is the water system? Are there any leaks and condensation? What about the furnishings and decorations and the sort of agents that have been used to polish them? What is the paint on the wall? What are the cleaning agents being used? And then we have, so this is the air quality, and then there is a simultaneous effect of the indoor environmental quality, which relates to acoustic conditions, lighting, the temperature, humidity and the visual comfort. All these sort of interact, and then it lead to the impact on the human health. And some of these symptoms could be irritation, then respiratory symptoms, which may be difficulty in breathing, fatigue and concentration difficulties, and headaches. So these are the symptoms. And what kind of diseases there may be? For example, asthma, lung cancer, cardiovascular diseases, chronic obstructive lung diseases, respiratory infections, and acute toxication are also possible in the extreme scenarios. So overall, our indoor air quality can be poor due to outdoor contaminants, movement indoors, inadequate ventilation or poorly designed ventilation systems, and the indoor sources themselves. Now when we look only at the home, we will go from bottom to top. So we can have first our garage, and in garage, through the exhaust of the cars or through whatever is kept in the garage, we can have carbon monoxide contamination of the air, gaseous compounds can be there, because of course the car also moves in. Then we could have solvents stored and therefore some VOCs in the air. Pesticides and herbicides, dust itself would be there, paints and other chemicals, and cleaning reagents or cleaning agents. So they may all be in the home environment. Then we will move a bit up, so then we are from garage, we are coming to inside, and for example, this house may have kitchen. So in kitchen we may have some odors or even chemicals, sometimes cleaning agent stores, or there may be lingering odors. Then some bacterial growth may be there if the food there is which is stale, and then some cooking pollutants might themselves be there, which what is being cooked and what is the fuel or the type of stove which is there to be and is being used. So these are the things here. Then we move up and come to the bathroom. Of course, bathroom is down also. So we are just looking at bathroom. In bathroom, we would have excess humidity, and then there would be personal hygiene products, including aerosols, different kinds of sprays. Also, some fragrances might be kept which would emit isoprene or terpenes. And since it is a bathroom, we may have mold spores as well. And sometimes cleaning agents are also there. Then we will come to the living room. In living room, sometimes there can be fireplace. So if a person is burning wood, you would have all the associated emissions from the wood. Then sofas, for example, we may have dust and dust mites. Different kinds of allergens might be there. There will also be some second-hand smoke which is possibly there in the living rooms. Then humidifiers might be there. Pet hair, again pet dander could be there, and then we may have carpets also in the living room. So these are our living room indoor sources. Then we come up and we come to the home office. This has a completely different set of emissions in that there may be printer and photocopiers which would emit ozone and volatile organic compounds. There may be also melamine furniture which may emit harmful vapors, VOCs and formaldehydes. This side we have the bedroom, and the bedroom might contain allergens, dust and dust mites, pet hair and dander, carbon dioxide, and again carpet. So all the emissions associated with these things might be coming in the bedroom as well. Then we will come to the attic, and here we may have asbestos sheets or old asbestos pipes. Then insulation material and associated chemicals might be there in the air, fiberglass, and then dust and dust mites might be there as well. So we have moved from bottom to top, and then below the ground floor we have basement, which can be often characterized with high humidity levels, which means there may be more mold or growth also possible. There are often unpleasant odors in the basement situation. We have molds, as I just said. Then carbon monoxide might also be there. It may be coming in and then being built up inside the basement. Then fireplace smoke might be happening, firewood related emissions. Then radon might be in the basements because through leakages maybe radon comes inside. Then we will have solvents being stored in the basement and all the associated emissions are possible. Wood stove might be there, dust and dust mites almost everywhere in the house. Then sometimes we may have boilers or some kind of gas heating systems. Often basements store paints and chemicals, so associated emissions of paints and chemicals might also be coming in. And then household cleaners, which are also possibly kept in garages and bathrooms, and lot of them might be in the basement, and especially those which may have more harmful or more strong odor, we might try to keep them in basement or at some inaccessible place in the house. But in those places there may be some possible sources happening. So the common pollutants in this indoor environment will go from here, we'll start with personal care products, which may have associated emissions of VOCs, volatile organic compounds, and then also semi-volatile organic compounds. And then building material will have VOCs emissions possibly happening. Then things related to people and animal, we may have CO2 emissions, we may have dust, bacteria, viruses, and pet allergens. There is again, as we said, exchange between indoor and outdoors. Then we will have furnishings, furnishings and textiles, which may often emit VOCs. Same goes for cleaning products. Cleaning products are also a good source or an important source of VOCs. Then we have fires and wood burning stoves, where CO, NO2, PM 2.5, VOCs and CO might be, the common pollutants associated with them. Then for gas stoves which are used for cooking, we have CO, NO, PM and VOCs. Now, since we have surfaces, there will also be a lot of surface deposition of pollutants. Then we come to boilers, and these boilers may be, emitting CO and NO2. Then in this area where we have kitchen, we have this exhaust fan, and here it's written basically mechanical ventilation. Mechanical ventilation can remove these pollutants from this area. Things such as candles, fresheners, air fresheners, diffusers, they often would be emitting VOCs to the air. And finally, we have the bathroom, where we also had these personal care products, and we will have molds and mildew happening in these areas. So these are different kinds of chemical and biological common pollutants. So, in the buildings, so we have here the different building types, different sources in those building types, and the common pollutants in those building types. So we have offices and public buildings where we can have HVAC systems, printers, building materials, smoking might be happening. There would be cleaning chemicals, so chemicals might be used for cleaning, and also people would be using personal care products such as fragrances and coming to office. And when they come to office, these are also sources. And the common pollutants would be PM, then VOCs, there is no apostrophe, it is just VO, volatile organic compounds, so VOCs. Particulate matter, VOCs, carbon monoxide, NOx and SO2. In basements and parking areas, we will have vehicular movement associated associated with this kind of settings. So here we would have emissions basically which are associated with vehicular pollution, and then when there are emissions in these basements or indoor or down parking areas, often there would be less ventilation in those areas. So we will have more PM, more VOCs, more carbon monoxide. We may have pH, other hydrocarbons, NOx and SO2. Finally, we have these public places such as places where we have construction activities. So in addition to the sources that are related to offices and public spaces, we will also have construction activities happening. But the contaminants are pretty much same, maybe in different amounts, which are PM, VOCs, CO, NOx and SO2. In densely populated buildings, often we may have decreased oxygen levels and increased carbon dioxide levels, and also temperature and humidity might be more, and also bioaerosols may be more, so because there may be emissions associated with humans happening in these buildings. So first thing was outdoor pollution impacting indoor. So our ambient air pollution is affected by meteorology, geography, topography, land use management, population density and location specific emission sources. So for example, in North India we have high population density, often high industrial activity, lot of transport and power generation. We have lot of crop residue burning, and also in some places we have dust storms, which are again source of lot of inorganic particulate matter also, a lot of mineral as well. So, in general, annual average concentrations of PM10, PM2.5 and NO2 are higher in northern India, and SO2 and maximum average ozone, so maximum daily average 8 hours, so MDA 8 ozone, are similar in north and south. So, here is a figure from this source, drawing the PM10 in the years 15, 16, 17, 18 and 19, and we have the guidelines from WHO and CPCB, and this is the PM10 concentration, often around 200 microgram per meter cube in North India, and in South India we have lower, although they still seem to be higher than the WHO and CPCB number. They are around 100 micrograms per meter cube. Same is for PM 2.5 in North India. We are around 100, actually around 50 to 150 micrograms per meter cube. Again, higher than the WHO and CPCB numbers. And in southern India, we have PM 2.5 more close to less than 50 to around 50. And in some instances, they are higher than the CPCB values. For example, here in some instances they are around the CPCB values in terms of median concentration. In terms of 75th percentile and the maximum value, they may be higher, but they are all sort of higher than the WHO numbers. SO2 values are somewhat similar in 2015, 16 to 19. If we see across these two figures, north and south, they are pretty much similar in magnitude, around 0 to 20, and with the median maybe around 10 micrograms per meter cube. And in terms of limits, sometimes the values go above limit, but most of the times they are down the limit, below the limit. For NO2, the values in North India are somewhat higher. If we compare yearly values, 15 here and 15 here, 2015 here, 2015 here, 2016, 16, 2017, 2017, 18 and 19. In all the cases, the NO2 values are somewhat higher in the north, and here this is a WHO number, and they are in some cases more than 50% values are higher, and otherwise they are lower. In southern India, mostly 75% values, which is the top of this box, 75% values are lower than the WHO limit. Then the maximum daily average 8-hour ozone is almost similar. You see the maximum in 17 around 101, in South India also about 100 and more. In 2015, our median is around 16 north, around 16 south. In 2016, the median is around 50 in the north and around 90 in the north. So in this case, actually southern India had more ozone. In 2017, the numbers were more or less similar or slightly higher in southern India. In 2018 and 19, we have the concentrations in the north slightly higher than concentrations in the south. So there is some difference between the north and the south. If we look at the seasonal values, we have higher PM10 during the winter months and lower during the summer months, and again we have higher in the winter months, and this is often due to this accumulation of PM 2.5. The meteorological conditions do not allow for efficient mixing in the vertical atmosphere. The values are substantially smaller in south. They show similar variation to the north, but the magnitude is lower. For example, in January, if we see in the south, PM 2.0 is less than 100 at least 75% of the time, and less than 200 75% of the time. Here that corresponding value is 300, and here the corresponding value is 250. So almost all the time the north will have a higher PM10 and higher PM 2.5 ambient concentration. and this also has an implication to the indoor air concentration. For SO2, the parameters are pretty much similar and the concentrations are also similar. For NO2, somewhat concentrations are the spread is higher in the northern India, but the magnitude is almost not too much different. And same for the ozone. So ozone is slightly higher in the north, especially in the April, May, June months compared to the south. PM matter dominates the pollution mix. The values can often become 150 to 100% of the corresponding guideline for North India, and they may exceed the guideline by 50% or 40% for the South India. And then there is some values for the 24-hour concentration measured in solid fuel using households, which become 500 to 2000, whereas in ambient air we have 300. So but just by using solid fuel we can elevate the concentrations a lot. If we look at the air pollution sources for particulate matter, residential activities are contributing a substantial amount, which is all commercial and residential cooking. Then we have transport and power and industries. So industries together are substantial. Then this is open biomass burning, agriculture activities. Then this is dust, anthropogenic dust. This is wind dust, is basically wind erosion. This is waste burning. So when we say residential activities such as cooking or burning of some kind of fossil fuel, we can do the contribution of indoor sources to PM 2.5, and it's looked like residential cooking for total relative contributions of biomass use for solid fuel cooking is a lot. It's this figure A. So almost more than 16% in the entire sort of Indo-Gangetic plain and a substantial part of South India. We have a lot of solid fuel cooking contributing to the biomass use. If we compare this to biomass used for lighting, for lighting purposes, almost everywhere the contribution is less than 2%, somewhat around 2 to 4% in the Indo-Gangetic plain, but that's about it. When we look for using biomass for heating water, there is still substantial, about 6 to 8 to 10 or 10 to 12% of the biomass is used in a lot of places in India, except maybe far north and west. And then for space heating, we have also this. So basically you can say this is during the cooler months, and there is a substantial use of biomass for space heating, especially in the Indo-Gangetic plain, which are generally quite they become quite cool. But the overall percent use would be about 8 to 10%. By far the maximum use, more than 16, 13, 14%, is for solid fuel cooking. So overwhelmingly biomass is used for in high proportions for solid fuel cooking in almost majority parts of India, reaching even up to 50%. When we look at the contribution to indoor sources, this is the population weighted mean concentrations of PM 2.5 in ambient air. And as you can see, the high regions of concentrations are in these states like UP, Bihar, then Haryana, somewhat in Rajasthan, then MP. Then we have a little bit less in Maharashtra, Odisha, and then lesser in the previous Andhra Pradesh, Karnataka, Tamil Nadu. And also this somewhat correlates with the proportion of population using solid fuels, which is high in Rajasthan, MP, then Bihar, and then also somewhat in UP and Himachal Pradesh. But in Himachal Pradesh there is sort of less particulate matter concentration relative to the biomass use or solid fuel use, whereas in south again in lot of places the proportion of solid fuel use is also low. So somewhat there is a relation, or it appears that places where we had more PM 2.5 concentration are often like the places which have somewhat more use of solid biomass fuel. So in 2007, deaths caused due to ambient air particulate matter pollution were 0.67 million, and due to household air pollution were 0.48 million in terms of the median value. So as you can see, household air pollution is actually causing a substantial amount of deaths when compared with the total ambient particulate matter pollution. In 2009, the deaths caused due to, or deaths estimated to be caused due to ambient PM pollution was 0.98 million, and for caused due to household air pollution was 0.61 million in terms of the medial values. So again, this is almost 60%. So household air pollution is a significant cause of such deaths. So indoor air pollution is responsible for death with the following health ailments such as ischemic heart diseases, pneumonia, chronic obstructive pulmonary diseases, stroke and lung cancer. Additionally, they may be also responsible for cognitive decline and may also result in mental disorders. We will cover a few case studies now very briefly. There was a case study here in the rural residential area around Pune, and the area of the house was typical 85 meters square, and with a median resident number of 5, 6 of the houses used LPG and 5 of them had smokers, and a lot of them were using sort of biomass based things. Some of them were using kerosene also. So when it was studied that what was the variation in particulate emissions, meaning what was actually the particulate concentrations with different changes in fuel type, when people were using a mix of biomass fuel, the PM10 was 73.8 micrograms per meter cube. This was a different types of mixes, could be rice husk plus biomass plus cow dung. When they were using biomass fuels, the concentration was still high, around 537. But when they used so-called cleaner fuels, which was LPG or even kerosene, the PM10 concentrations were quite lower compared to previously, less than 200, so 196 microgram per meter cube. Same for PM2.5, the cleaner fuel had much lower PM2.5 values. People or places where cleaner fuel were used had much lower PM2.5 values compared to places where biomasses were used and where a mix of substances were used for cooking. In different types of, it was also clearly found for PM10 especially, the biomass had the most concentration. But when the areas were using biomass fuels, the indoor air had most of the indoor air was most when biomass PM10 was most when biomass chula were used. The PM10 concentrations were much lower when kerosene was used, median 147 and sort of high value of 204. Similar to the LPG use, which was 170 median and 200 maximum. When PM2.5 was used, the biomass use had led to PM2.5 of 140, but kerosene and LPG, the PM2.5 concentrations were 74 or 107, so much lower than those observed while biomass was used. So as we see, different types of biomass in general lead to higher at least PM10 and in some cases also PM2.5. In this case the median was 84, which is somewhat similar to 74 and lower than 100, but the maximum was 420 in PM 2.5 range, which is higher than 122 and higher than 127. So in general, the indoor air quality in terms of PM10 and PM 2.5 was the worst when biomass chula were used, and this quality in terms of PM10 and PM 2.5 substantially improved when kerosene or LPG were used. So these two look to be clean, sort of cleaner fuels compared to biomass when it comes to indoor PM pollution due to cooking sources. So again, it was looked at what was the PM 2.5 contribution to PM10, and dung cakes and wood plus kerosene, and dung cakes were plus wood as fuel contributed when these fuels were used. PM contributed around 65% of 65% to PM10, and when kerosene and LPG were used, PM 2.5 was about 48 to 53% of PM10. And in terms of when the firewood was used, there was much lower PM 2.5 in the PM10 fraction. And so most of the numbers you would say were in the PM fraction more than with 2.5 micrometer. In another case study, which was taken in the rural area of Burdwan, various concentrations of CO2 and O3 were observed when there were different types of fuel types being used. In general, dung and straw led to the maximum CO production, dung, straw and wood, whereas leaf, coal cake, twigs produce much lower CO, and when gas stove was used, the CO concentrations were actually much lower. Similarly, we see when in terms of CO2 emissions, dung use and leaf use and coal cake use and twigs, look, they were all high. Straw burning led to a bit lower CO2, and the least CO2 was led when gas stove were used. Similar observations were also seen for ozone. When dung was used or wood was used, and twigs were used, the ozone concentrations were high, and these again decreased substantially when gas stoves were used. So gas stoves seem to be very clean cooking mechanisms. Here we will see this in the similar pattern. In this place, they have compared the average concentrations in living room and the kitchen, and we see in terms of CO, almost similar values in kitchen and living room. The kitchen had somewhat band, like slightly they were going above 0, whereas in living room they were not, almost always close to 0. Ozone values were low in both the cases. Humidity was high in the living room because people would be sitting there and talking. In kitchen, the air itself might be a bit more heated. And then the main difference was in CO2 concentrations, because in kitchen you would have emissions due to sources, but only 1-2 people will be there, and in living room lot of people might be sitting. Sometimes they may close the window also. So there would be a CO2 buildup in the living room in this study. Finally, we are going to do another case study on a university campus. So university campus are very unique places, and a lot of activities are happening. First thing is, if it is a campus being built, or campus which has recently seen construction activities, construction would lead to like emissions of dust and deposition of dust very close to different places in the university, or sometimes it will lead to a higher PM in concentration in the outdoor air itself. Now in the indoor environment of the university, one can have classrooms where people are using chalk, and also students and people are walking in and out. In a computer room, we will have things like printers and associated equipment which may lead to PM emissions and also emissions of other compounds. Then we will have gym where there will be PM emissions and also bioaerosol emissions. And then the dining hall where we will have people coming in and out, and also a lot of cooking taking place. So in general, university campuses will have a very variety of emission possible. So in a case study in a university environment in India, the researchers studied classrooms of which there were like small classrooms, air conditioned and less ventilated from outside or less open to the outside air, and then one classroom which was naturally ventilated. Then one lecture hall was studied. Then one coffee shop was studied in which one door was generally closed. The coffee shop actually had one door and it was mostly kept closed, and the coffee shop was air conditioned. Then we had a computer room which was also like, there would be a door but generally kept closed, because often in computer rooms you want to have cooler temperatures, so people will have AC, and the exit points of air would be closed so that cool air can build up. So there was one door but it was mostly kept closed. Then in this setting there was a gym which was not air conditioned in this study, and it had 2 doors and 5 windows, so no AC and also chances of ventilation. Then there is a dining hall which serves like hundreds to thousands of students. Then there was a semi-open canteen which was like a group of shops. So this semi-open canteen was in an alley with other shops such as saloon and printer shops. And then there was like a open coffee shop which was open on 4 sides and only had a roof on the top, but otherwise from 4 sides it was open to the outdoor air. The results were found in which PM1, so particulate matter less than 1 micrometer, was maximum in the closed coffee shop, followed by the sort of normally closed air conditioned classroom, followed by the classroom with natural ventilation, then computer room, gym, then lecture hall, and then dining hall. So mostly these areas had the PM1 or particulate matter quite a bit in the lower than 1 fraction, which means we are looking at ultrafine aerosols. PM 2.5 also followed somewhat similar pattern, except the computer room and classroom with natural ventilation switched positions. In contrast, PM 10 was maximum in the dining hall, and likely this was due to like the outdoor dust coming in, because the area outside the dining hall was mostly like just mud, red mud. Also, people might be bringing this mud inside, and then when they are walking about, this dust is being resuspended. Then we had computer room, coffee shop, gym, and then classrooms and lecture hall. We also studied the changes in PM concentrations with activity of people. So if we see here, when we look at the dining hall, there were concentrations if PM1 were much lower when the dining hall was occupied compared to when it was occupied. Then same goes for PM 2.5 and PM 10, and then total suspended particles. So there was a significant difference between the PM different particulate matter fractions. The star means significant difference when the dining hall was occupied compared to when it was unoccupied. So likely people were, 1, bringing dust inside, 2, when they were walking, the dust was getting resuspended. In the AC, air conditioned small classroom, there was also significant difference between indoor and difference between different PM fractions when the room was occupied versus unoccupied. So again, people were coming in, maybe they were resuspending the dust, and this led to significant difference between the unoccupied and occupied. But when we had the classroom with natural ventilation, there was no significant difference in all the PM size fractions, regardless when the room was occupied or the classroom was not occupied. And this makes sense because the natural ventilation was able to maintain the exchange of particles between indoor and outdoors, and so that there was no extra buildup indoors. And in this way we see lecture halls, and it clearly shows that indoor PM was correlated with indoor PM 2.5, indoor PM 1 was correlated with indoor PM 2.5, PM 10 and TSP, and these were actually correlated with some values outdoors. So indoor TSP was correlated with outdoor TSP. Indoor PM10 was also correlated with outdoor PM10. Then indoor PM total suspended particles was correlated with the outdoor values. So there was a lot of correlation between indoor and outdoor values, suggesting that outdoor air was contributing to the indoor air, and the indoor air was sort of the variation in the indoor air was related to the variation in the outdoor air. But when we looked at the AC classroom or the coffee shop, which was air conditioned, had one door which was mostly closed, there was no correlation between the indoor PM and outdoor PM. See, there is no shaded matter. Same here, indoor PM versus outdoor. And indoor PM concentrations in any fraction were strongly correlated with indoor PM fractions in concentrations of indoor PM fractions in other size fractions. For example, indoor PM1 concentration was significantly related with indoor PM 2.5 concentration, and indoor PM1 was also significantly correlated with indoor PM10. Indoor PM1 was significantly correlated with indoor PM TSP, and this was observed for all of them. So there were all the indoor PM concentrations were correlated with each other, but none of them were correlated with the outdoor values, which means there was a disconnection between the outdoor air and indoor air in the air conditioned classroom, which had one door which was mostly closed. So there was a disconnection between outdoor variation and indoor variation. Same for our coffee shop, which was mostly kept closed. There was indoor sources, and the indoor PM size fraction concentrations were quite correlated with the corresponding concentrations in the other size fractions indoors, but there was no correlation with the outdoor value, which means again there was a disconnection. It had its own sources which behaved independently regardless of what was happening outside. Lecture hall, we have already seen that there was a correlation, and in dining hall also there was a significant correlation in a lot of indoor PM and outdoor PM, which suggests for the sitting area in the dining hall there was a substantial influence of the outdoor air quality on the indoor air quality. Finally, CO, carbon monoxide, was also measured, and in all the places there was some CO in the air conditioned classroom, 0.45 ppm, which ranged from without detection, below detection limit, to 2.63 ppm. These values were present compared to so many other settings. For example, the classroom with natural ventilation did not have any CO detectable. Lecture hall, the closed coffee shop, computer room, gym, semi-open canteen and cafeteria, in terms of median value, none of the detection took place for CO. The only place where CO was substantially found was in the dining hall, which had a median of 4.5 ppm and the range between 0.76 to 6.9 ppm. So clearly, dining hall had a confirmed presence of carbon monoxide, and this is most likely due to the cooking activities which may be releasing CO in the cooking area, and then this CO, as CO behaves quite similar to air, it is probably also then coming outside to place in the sitting area where the sampling was conducted. So it was clear that in some settings the outdoor air was contributing to indoor air when we were looking at lecture hall and several other areas, when indoor PM in any size fraction was correlated with the outdoor PM in these different size fractions. But in some cases the indoor PM value was disconnected from the outdoor value, such as in the closed classroom with AC, and also the closed meaning shops in which the door is mostly closed, the closed coffee shop with AC, and in the dining room, the PM were the indoor PM were correlated with the outdoor PM, meaning people were, there was the PM was coming through the air, and also the students might be walking in and out, so they might be bringing outdoor air to inside, and the inside walking then resuspends the dust. In dining hall is the place we found a substantial CO as well, which is basically due to our cooking activity, and here we had a confirmed, or there was a strong chance that this is a indoor, it suggests strongly that in this case, in terms of CO, the indoor source is dominant, because and nowhere else is this source important other than in place where there is cooking happening, which is our dining hall. So in summary, sampling sites are impacted by cooking, such as dining hall, and they may also have higher PM than other sites, such as in classroom, gyms or cafeterias. Resuspension of dust from people's movements is an important source of PM. There is a direct contribution of outdoor air to indoor air quality near sites such as construction area, barren lines and unpaved roads, and CO concentrations can be high in the dining facilities.